Okay, so we'll get started. So let me just recall where we were at last time. Well, when we ended, we were basically in the middle of showing that cyclotomic polynomials are irreducible. So recall the cyclotomic polynomial, Vn. This is the polynomial whose roots are the primitive nth roots of unity. So we literally started out just by writing down the primitive nth roots of unity in terms of like the exponentials, like either 2 pi I k over n, where k and n are co-prime, and the complex numbers, and then sort of declaring this to be a polynomial with those roots. But later we saw sort of, and we also wrote down some different ways you can define this just purely in terms of integer polynomials. And in particular, in the sense that the roots of this polynomial are primitive nth roots units, or make sense in somehow over any field. Over any field, if you have a root of this polynomial, then it's sort of something such that x to the n is equal, or any field sort of characteristic coprime to n. Then this is true. Okay. Right. Well, we're in the middle of showing it in the sense that we finished showing this, but we are kind of rushed at the end. So I just wanted to go back over, and then this last argument at the end is sort of a very interesting argument. So I want to go back over this, and then we'll build on that a little bit to talk more about Galois groups of polynomials and we'll talk about some related things. Okay, so what was the key step in the argument? And I'm going to state it in a sort of different way. State so the main observation in a different way, like in more generality. And so not just for cyclotomic polynomials, but sort of for any sort of for more general polynomials of integer coefficients, and then we'll specialize to sort of how this helped us here. So the observation was essentially the following. So let f of x, I'm just going to take this to be a monic polynomial of integer coefficients. I'm not going to assume it's irreducible. Okay, and then I'm going to let, so degree n. I will assume it's separable. Okay, and so, good, and then I'm going to let alpha 1 through alpha n be the roots, excuse me, of f in the complex numbers. Okay, and so then I can do the following sort of silly thing. I can look at just the ring I get by adjoining sort of alpha 1 through alpha n to the integers, so sort of inside of C. So this just means the smallest subring containing the integers and these roots. Okay. So this is a non-zero ring. So let me take in fact, sort of how to say this. Essentially, because f is monic, you can show that so for any p, so for any prime p, there is a map from sort of, so let me call this sort of R, from R to fp bar. So where fp bar is just some algebraic closure of fp. Okay. Essentially, the idea is like I mean, first mod out by P, and then you're going to get some ring. And so you have to say something to deduce that the P is not in the maximal ideal. Like, sorry, you have to know that P is not invertible in this ring. But sort of the condition that this polynomial was monic integer is enough to, so you can, as monic integer coefficients, like that's enough to sort of tell you that P is not going to be invertible in this ring R. And so you take R mod P, you just take a maximal ideal in R mod P. R mod P. So that's going to give you a field. I mean, it's going to give you. Somehow, there are different ways I can say it. Like it's going to give you an algebra, like a finite extension. So then, so R mod P mod M is a finite extension of FP. And somehow the point is this extension is going to be generated by the elements alpha 1 through alpha n, which are all algebraic, so by the images of those elements in R mod P. So anyway, so just alpha 1 bar through alpha n bar for the images of these in R mod P. Okay, and then, so then you sort of mod by max ideal, and then maybe I better just write alpha 1 through alpha n, because I'm going to use alpha 1 through alpha n bar for something else. So the point is, like, this gives you a way to sort of extend, like, this map from R to FP bar sort of extends reduction mod P on the integers. And so there's some ideal up here whose intersection with integers is P, so this is reduction mod. Sometimes I write this thing like Gothic P. So there's some maximal ideal in this ring R, such that when you reduce out that maximal ideal, you get something in FP bar. Okay. So that's the idea. So you've somehow extended your ability to reduce mod P from just the integers to this ring R. And there are some choices involved. Like, there's not sort of a unique way to make this choice. And at some point I said, take a maximal ideal, but fine, who cares? Like, I'm all this argument I'm about to say is, and everything that's only going to just require that you have some choice. It doesn't matter what this choice is. Okay. And so, so we're going to write F bar in FPX for the reduction of F mod P. So F was this polynomial we started with, that integer coefficient, so I just reduced those coefficients mod P. And then, so, F is equal to x minus alpha 1 times x minus alpha n, which is sort of in polynomials over the complex numbers, but also this is really in polynomials over our ring R, because alpha 1 through alpha n are in this ring R. So this is a polynomial of coefficients in R. And so then I can take this to sort of, and then if I sort of reduce mod P, like this goes to F bar equals x minus alpha 1 bar. Yeah, so I'm sort of going to I'll call this map, I'll still write as R goes to R bar. So this sort of extension of reduction mod P to this ring R. And so that means sort of Well, I mean, the roots of f get mapped to like the roots, these alpha 1 to alpha n to get mapped to the roots of sort of f bar, sort of under this reduction. And so if f bar, so this is a character, this is some polynomial in fpx. So if this is separate, sorry, 1 second. So if this polynomial is separable, so I knew f was separable, but like, of course, like when you reduce mod p, like you might not still be separable. But if this reduction mod p is separable, then like alpha 1 bar through alpha n bar are distinct because they're roots of the separable polynomial. And so what that means is sort of you have sort of R living inside the complex numbers, and then also sort of mapping by this reduction map to fp bar. And this is setting up a bijection between, this sets up a bijection between, so all right here, like we have this set alpha 1 through alpha n in the complex numbers. And so by definition, those live in R. So that's how we define R, like R, just the smallest ring containing those. And then these are in bijection with the roots with these alpha 1 bar through alpha n bar, just because these are all distinct things. So this is still a set of n elements. And this is the roots of f bar in sort of fp bar. And this is the roots of f in the complex numbers. Okay. So there's a bijection between these things. So produced in this way. Okay, now what's the main thing about this bijection? So I mean, somehow like this, I mean, this bijection sort of is compatible with the following, like if g of x in z of x is a factor of f of x, then the bijection preserves roots. Like, so the bijection sends roots of g bar of x sort of in bijection with sort of in fp bar with roots of f of x. So it's the roots of f of x in C. So just by in the same argument, I mean, like the polynomial g is sort of some product of sort of these linear terms, and then sort of those get sort of mapped to the roots of g bar and to the roots of g. So I mean, somehow you get this way to understand the roots of this polynomial in the complex numbers in terms of roots of the polynomial in the in over fp. So this is very powerful. And so how do we use this? So to show phi n of x is irreducible, okay. So how do we do this? Well, we say let g of x. So and first, so we have this bijection. So here the roots, like, okay, let me write zeta, the roots in C. So if I write zeta is equal to e to the 2 pi I over n, the roots in C are just sort of set zeta to the k, where k is in z mod nz cross. So those are the roots of phi n of x. And then if I sort of, so I'm going to take p not dividing n, let me take any p coprime to n, then sort of the above sort of, so then the reduction of phi is separable. And just because then x to the n minus 1 is already separable. So phi n is sort of in particular divisor of x to the n minus 1. So because the product's all primitive roots of unity, so in particular, they're all roots of unity, nth roots of unity. And x to the n minus 1 is separable. Just then you take its derivative, it's n times x to the n minus 1. So as long as n is not 0, that's not. Not as long as n is non-zero, then the only roots of that are 0. But 0 is sort of not a root of this thing. So this is sort of an argument we already saw. This polynomial is separable. Okay. So if I take, so good. So I'm going to take that, and then so I get this bijection with roots in FP bar. And again, these are going to be zeta to the, so I'll just write as zeta bar to the k and z1 and z cross. So, and the reason this, and so really what I wrote above would be like zeta to the k bar. So I'd sort of put the bar after raising the kth power. But this map is sort of a stat, like this map comes from a ring isomorphism, like from maps of rings. So like if I sort of have one of, like if one of these roots happens to be a kth power of another root, then sort of that's compatible with this reduction map. So and the point, and just explain this sort of subtle point that zeta bar to the k is equal to zeta to the k bar. Okay, so we have this bijection between these roots, these sort of different sets. Okay, so now I have G. So now suppose so now suppose zeta to the k is a root of G. So G is this irreducible factor of sorry, I don't think I fixed that yet. So this is an irreducible factor of the n of x. Okay, so then sort of zeta bar to the k is a root of sort of G bar. But then, I mean, G bar is an FP x. So if I apply the Frobenius automorphism to this root of G bar, this is also a root of G bar. So, and G bar might not be irreducible still. There's no reason it has to be, but like, nonetheless, like this is true. Like if I have a polynomial FP of x and I apply sort of some automorphism of FP bar that fixes, like I apply its Frobenius automorphism, like it sends roots of G bar to roots of G bar. Right? It sends roots of any polynomial of coefficient FP of x to roots of that polynomial. Just because it's an automorphism fixing FP. Okay, but this is just zeta bar to the k to the p. So zeta bar to kp, which is equal to zeta to kp bar. So thus, but if this is a root of G bar, that means, by what I said above, that zeta to the kp is a root of G. Okay. But now, I mean, sort of, and this applied sort of for any root of G, and sort of any p not dividing n, what's that exactly means? So like if zeta to k is a root, so let me say like if zeta to k, yeah, I mean, so if zeta to k is a root of g, then so is zeta to k to the p, and then I apply sort of the same thing to zeta to k to the p, which I now know is a root, and so I get zeta to k to the p squared, and then like, and then sort of if I know like zeta to k to the p squared is a root, and I take some different prime p, like different prime q, so zeta to k p squared q for some other prime q, and so on. So I can just repeat, and when I see, but in primes not equal to so primes not dividing n generate z mod n z cross. So this would be zeta to k, and this is supposed to be where's the so the primes not dividing n generates z mod n z cross. So once you have one root, so once you have one root, you have all of them. So you've done this very clever thing in this argument because you've, and it's not, and again, like, it's not true. Like you're not saying that g bar is irreducible mod p. Like when you take this polynomial g and you reduce it mod p, what you get is reducible. But like it still has sort of some smaller irreducible factors. And like then you're using sort of the information you get sort of by looking at those and sort of varying over all the different primes p in order to conclude that sort of g itself has to be irreducible. And so this is sort of, this is more delicate than sort of a kind of argument that might be more familiar where sort of you take a polynomial and like say it's irreducible because like a polynomial z is irreducible if its reduction mod p is irreducible. But like that's not what we're saying here. We're using reduction mod different primes p and Galois theory to sort of to do this. I mean, so I mean somehow, and let me just say like the key points that make this work. And this doesn't work for other polynomials besides the cyclic polynomials, essentially because and so well, first key point is like the Frobenius is sort of an algebraic, is sort of expressed. So it's an algebraic map. So like most field automorphisms, like they're not, I mean somehow they're not algebraic, like they're not expressed, but like they're not the form like x goes to x to the p. Like so it's like, so let me say this way, then let's say it's polynomial. So the point that the Frobenius automorphism of the polynomial map is sort of important here. And then sort of, and the point that sort of roots of unity are powers of each other. So in sort of, in other words, like the roots of x to the n minus 1 satisfy lots of algebraic relations. So somehow these are sort of the two things that are like making this sort of work. And like, and you can just imagine sort of trying to run, yeah. So like you imagine trying to run this argument for a different polynomial. Like everything I said sort of in this light pink would be fine. Like you still would get a bijection between, at least like for all the p where sort of f bar was not separable, where f bar was separable, you'd still get a bijection between the roots of the complex numbers and roots over F bar. And it'd still be true, like if you sort of had some, like you started with some irreducible factor G. Yes, you could start with some irreducible factor G of F, and now then you could take sort of alpha, like then alpha 1 bar to the P would still be an irreducible, would be a root. Like if alpha 1 was a root of G, then alpha 1 bar to the P would be root of G bar. But where you'd run into trouble is that like you wouldn't know, like alpha 1 bar to the P, like you're not going to know sort of which, without sort of much more information, you're not going to know which of these other roots reduces to alpha 1 bar to the P. Like, because alpha 1 to the P is not typically going to be one of these roots. So you're going to have to sort of identify something that's not alpha 1 to the P, but is sort of like reduces to alpha 1 to the P mod P in here. So this is somehow where this like argument trips up if you try and sort of if you tried to do this for like some other polynomial. And finding sort of which of these roots reduces to like alpha bar to the P. Michael, were you going to ask a question? Yeah. So it's just because, so like it's a factor, phi n is a factor of x to n minus 1. So it suffices to show x to n minus 1 is separable. And because the derivative is n times x to the n, or so the derivative is n to the x to the n minus 1. And so if n is not equal to 0, then the only root is 0, which is sort of not a root of x to n minus 1. So it's like, and here you have to be careful. And it's tempting to just say, well, this is not irreducible. So you can't just say this is not 0. You really have to say this is co-prime to x to the n minus 1. But this is really co-prime to x to n minus 1, as long as n is not 0. Okay, great. So and nonetheless, in this basic observation is going to turn out, this basic observation that you can sort of relate roots of a polynomial, like roots in the complex numbers to roots mod P, is going to like, it actually, like, even though it doesn't work quite as well for other polynomials, the cyclotomic polynomials, it still ends up being like the most effective way we have of computing Galois groups. So I was going to, yeah, let me just go, and I think actually makes sense to probably just say that now. So reorder, sorry, you can't tell I'm reordering, but I'm just reordering how I thought I was going to do this. So I'll say like this doesn't work as well for other polynomials. But so if it does still give something. So basically, the result you get is, so this is coming from the argument above, plus just a little bit of algebraic number theory. Which I won't get into, but it's not so, the sort of epsilon more you need is not so complicated. But it doesn't immediately follow from what's above. You need to know a little bit more than what I said above. And so, but you get the following. You get if f is a polynomial with integer coefficients, is a monic, inseparable. And P is a prime such that F bar, by which I mean F mod P, so you just reduce coefficients mod P, is separable. Then the Galois group of F contains a so it contains a permutation. So when you say the Galois group of a polynomial, and what do you mean? You mean the splitting field, like you mean the Galois group of a splitting field thought of as a subgroup of the symmetric group of this. There's a subgroup of the permutation group on the roots of that polynomial. So like this is equal to the Galois group of the splitting field of a splitting field as a permutation group on the roots of F. So if I fix a, like if I take a splitting field, then it makes sense for me to not only take the Galois group of that splitting field, which is sort of the automorphism group of the extension, but also in that automorphism group acts faithfully on the roots of F. And so I can think of it as being a subgroup of the symmetric group on the roots of F. Okay, so when I say containing a permutation, I mean sort of in that sense, like containing a permutation of the roots. So the statement is that the Galois group of F contains a permutation of cycle type K1 K sort of M, where F bar is equal to sort of F1 bar times Fm bar, the degree of Fi. So these are irreducibles in Fpx. The degree of Fi is Ki. So, I mean, another way to think about this is like, so the Galois group of F bar, and so this in the Galois group of F bar is generated by the Frobenius element, and sort of this cycle is just Frobenius acting on those roots. And so the roots of F bar. So like, and if, so you find, and Frobenius acting on the roots of a polynomial, and somehow, and you think about this, but so this is sort of an easy exercise in like the Galois theory over a finite field. Like if you sort of take the Galois group of a polynomial finite field, like Frobenius just acts by sort of this type of cycle. Okay, so in the argument in sort of an algebraic number theory that you need is then the sort of fact that like you can sort of lift the Frobenius automorphism in characteristic P to sort of some automorphism in characteristic 0. So that's sort of something that needs to be proved. So that's sort of the epsilon we didn't prove. Okay, so this is the statement, but this is very powerful, especially if you want to show a Galois group is big. So, so like, let me just say like an example of how you can use this. So let me say, okay. So application of this result. So for every n, there exists a degree n polynomial. It's going to be irreducible in Zx such that such that the Galois group of F is just the symmetric group. So it's as big as possible. So how do you do that? Well, and so before, like when we were doing cyclotomic polynomials, we were starting out with, like when we did this irreducible cyclotomic polynomials, we were starting out with a polynomial we wanted to understand, and we were like using its reduction y different times p to understand a specific polynomial. Here, we're going to take this theorem and sort of use it to reverse engineer. So let me say the idea. So reverse engineer using the theorem. Because, well, the thing is, like, you guys already know some conditions on sort of cycles that guarantee that will like generate the symmetric group. So we know from a previous homework, a 2-cycle, so a 2-cycle and a n-1 cycle generate Sn. Well, okay. I'm pretty sure we proved this, or we might have proved, we proved a couple of different sort of related things. This one is true, and if we didn't prove it, you can sort of substitute what I do next for some related one. So, okay, so I'm going to take f sub 2 of x and f2 of x to be any degree n irreducible. I'm going to take f3 sub x in f, so this is a polynomial of coefficients in f3, to factor as a degree 2 irreducible times irreducibles of odd degree. I mean, this is certainly possible, and somehow we know times sort of distinct irreducibles of odd degree. So you should think to yourself why it's possible to choose distinct ones, but this is not so bad. Okay, and then I can just take sort of a degree, and if n is odd, then I can just take sort of a degree n-2 irreducible, or if n is even, I can take a sort of a degree n-1 irreducible and a degree 1 irreducible. Okay, and we know just from the Galois theory of finite field, like we know for every finite field there exists an irreducible polynomial of every degree, just because there exists a degree n extension of every degree. So like these, we know these exist, and then take sort of f5 of x to factor as a degree n-1 irreducible times a linear factor. Okay, so these are 3 degree n monic polynomials with coefficients of different fields. But I can just use, I mean, the Chinese remainder theorem says there exists an f contains ex, or monic, with f mod 2 is equal to f2, f mod 3 is equal to f3, and f mod 5 is equal to f5. So here I'm just reducing, and when I say f mod 2, I mean just reduce the coefficients mod 2. And the point is, like, just for each degree, like let me look at the coefficient and apply the Chinese remainder theorem, which tells me sort of I can sort of find some integer in Z that's sort of congruent to sort of the things I've sort of chosen to be mod 2, mod 3, and mod 5. So I just do it sort of each coefficient at a time. Okay, and so that tells you you get a polynomial f, the polynomial f, sort of whose reduction. Yeah, so so whose reduction mod 2 is irreducible. So f is itself irreducible. Okay, so maybe I can add that too. And so somehow there's a little bit redundant information. So, but anyway, let me add it here. There's an irreducible degree n polynomial. Okay, so f is irreducible. It contains a 2-cycle, and it contains sort of from this one. So, and here, sort of the cycle type is sort of 2, and then sort of a bunch of odd degree things. And I could take these, and you can't take these all to be linear factors because I'm working over f3 of x. So I need these to be distinct because I want the polynomial to be separable. But anyway, there are a bunch of odd degree things. And so if I raise this, if I raise this cycle, I get to a suitable power. So there's 2 cycles coming from f3, and the n-1 cycle is from f5, and the theorem. And so, the point is, sort of, you get a cycle is sort of is a transposition and a bunch of odd length cycles, and you just raise that to a suitable odd power, and all that you're left with is a transposition. So this transposition, it's a raise to a suitable odd power. So you're raising the thing this theorem is giving you. So a theorem is giving you like say you had like a degree 2 times a degree 5 thing. So the theorem is giving you sort of something that's sort of a 2 cycle times a 5 cycle. But you raise that to the 5th power, and you're just left, like the 5 cycle goes away, and you're just left with the 2 cycle. So that's sort of what I'm saying here. Good. Okay. So then, but that produces a polynomial f. And then you would even, and this is fairly effective. And you could, if you had some specific n, if you had some specific number n that you wanted to sort of find a polynomial of degree n that has the Galois group, the symmetric group, then you could implement this. You could implement this strategy. Sort of, the Chinese remainder theorem is fairly efficient, and you can just sort of do a search for irreducible polynomials and so on. It's not, it's sort of, it is computable, even. So this is sort of another nice illustration of how you can use this sort of mod p reduction in a powerful way. Why don't we take a break, and then also we'll shift gears a little bit. We'll stop. We're still going to talk about Galois groups of polynomials, but I'm going to sort of shift back away from these sort of mod p methods and sort of just talk about some other aspects of the theory for the rest today. So let's start again at 115. Okay, so I'm going to do a more concrete example. So this and it's not unrelated to what we were just doing with prime numbers, but instead, sort of, in this example, we're going to use we're somehow going to use the real numbers in the same way we're using excuse me, in the same way we're using finite fields in the last example. So this is and maybe will be helpful for understanding a little bit what's going on in the finite field case too. So, okay, so look at this polynomial, x to the 5th minus 6x plus 3. And so this, the claim is this has Galois group S5. So, well, first, I claim it's irreducible. Can someone tell me why it's irreducible? Yeah, great. So irreducible by Eisenstein at 3. Okay, so that's an easy win. Great. So 2, I claim there are 3 real roots and 2 complex and sort of 2 non-real roots in C. So I take the sort of roots in the complex numbers. I claim there are three of them are real and sort of 2 of them are not real. Okay, so why is this? Well, if I supply intermediate value, so I'm not going to do the computation, but I'll just say what it is. So if I do the intermediate value theorem, sorry, between -2 and 0, then between 0 and 1, and then between 1 and 2, I find sort of a root, and a root. So I get at least 3 real roots. The point is sort of when you're going negative, positive, negative, positive when you do this. So sort of in between each of these, you're going to get a root. So that gives me at least 3 real roots. On the other hand, so if I write f of x is this guy, then the derivative of x is 5x to the 4th minus 6. Okay, and it's not too hard to see. This only has 2 real roots. And so now the roots are sort of, I take a 4th root of 6/5, and then sort of I spin it around. So I take I, like plus or minus I, plus or minus O. So the 2 real roots are plus or minus the 4th positive real root of 6/5. So that means the derivative can only be 0 twice. But all of these roots are simple roots, and this polynomial is separable, so all of the roots are simple roots. Separable. I mean, in particular, it's irreducible, so it's always separable. So all the roots are simple. So that means, sort of between any 2 real roots. So the mean value theorem. So we get to use both the intermediate value theorem and the mean value theorem. So a fun calculus application gives root of f prime. Okay, so between any roots of f, there's a root of f prime. Between any real roots of f, there's a real root of f prime. But that means if you have 4 roots of f, if you have 4 real roots of f, then you'd have 3 real roots of f prime, which are contradicting that we only have 2. Okay, so good. So that implies there are at most 3 roots, 3 real roots of f. So we get a fun application of calculus to sort of understand the number of real roots. But if there are only 3 real roots, then there have to be sort of a pair of complex conjugate complex roots. So okay, has a pair of complex conjugate complex roots. Okay, so So if I write G for the Galois group, which I can think of sort of the automorphisms of sort of K over Q, where K is the splitting field of F in the complex numbers. So it's just a field, subfield of complex numbers generated by the roots. Then 1 implies, okay, so this polynomial is irreducible. That means the degree of sort of extension where you add 1 root is 5. So that means sort of the degree of the splitting field is divisible by 5. So that means the Galois group has order divisible by 5. On the other hand, sort of G is, okay, so G has an element of order 5. But G is a subgroup of S5. So that implies G has a 5 cycle. So here I use the Lagrange theorem. So this is a prime order. So there's a prime number divided the order. So that means there's an element of that order. But I mean, because you're a subgroup of S5, that means it's a 5 cycle. So good. So G contains a 5 cycle. And then 2 implies G contains a transposition. Okay, well, easy enough. G yeah, just complex conjugation. So in complex conjugation, the complex numbers, I mean, it's some automorphism of the complex numbers that fixes the real numbers. So in particular, it fixes the rational numbers, but also sort of it has to fix sort of any splitting field inside of it. So it fixes K. So complex conjugation sort of restricts to an automorphism of K. And we know exactly like sort of, well, the 3 real roots, it does nothing to them, it just fixes them. And then the two complex conjugate roots get swapped. So this gives a transposition. Okay, so G is S5. Because S5 is generated by a transposition and a 5 cycle. Check. So in here, and this is just like what we were doing somehow over when we were in this, we're using the real numbers here in the same way we're using a finite field. I mean, we're using the factorization of this polynomial F over the real numbers, plus the fact that so the Galois group of real numbers sort of has this distinguished generator, sort of just complex conjugation, in order to get sort of some element of a specific cycle type in our Galois group. So it's sort of the exact same kind of argument, just maybe this feels a little bit more concrete because, I mean, somehow everything was living inside of the complex numbers instead of like doing this reduction mod P map. This sort of feels more lossy. Okay. But somehow, I mean, being able to do reduction mod P is much more powerful because there are many more primes. And somehow there's not the same restrictions. Like, I mean, arguing with real numbers, like you're only going to get elements of order 2 in the Galois group, just because sort of the Galois group of the complex numbers of the real numbers sort of is sort of generated by complex conjugation, which has degree 2, which has order 2. So somehow you can only use the real numbers to get a transposition at best, or like a sort of a product of transpositions. Whereas you can really, using these different finite fields, you can really sort of get other interesting cycle types. Yeah, okay, good. So that's that example. I mean, yeah, so maybe for doing these examples and talking about how to compute the Galois groups of polynomials and seeing some applications, and maybe the right question now is to ask sort of, what is the Galois group of a polynomial? Like, what is it measuring? So like, so me just say, so we've seen some of those examples now. So so the Galois group of x to the n minus 1. So it's the same as the Galois group of phi n. And this is sort of small. Just because in the Galois group of any polynomial is going to be some subgroup of like a degree n polynomial is going to be a subgroup of the symmetric group of Sn. And so sort of Z mod n z cross is for a pretty small subgroup of Sn. Whereas generically, I'll say what I mean by it. So I don't know if you just work. So this is all over Q. Generically, Galois group of a degree n polynomial is the full symmetric group. Okay, so what do I mean by this? Well, first, I've just argued that there are plenty of examples of degree n polynomials whose Galois group is a symmetric group using this like sort of Frobenius, this mod p reduction trick. So we've seen a way to produce some polynomials. On the other hand, you have an exercise in your homework this week, or sorry, a problem on your homework this week. So this problem about symmetric polynomials, and this problem about symmetric polynomials, like it essentially says, like if you treat the coefficients of your polynomial as variables themselves, then the Galois group is the symmetric group. So this isn't quite what the exercise says is written. The exercise sort of thing in invariant theory, there's one extra thing you'd have to add from transcendence theory to what's written on the exercise that I don't want to sort of get into. But there's a pretty simple extension of the exercise as written says that sort of if you just treat the coefficients of a polynomial as variables, then sort of the Galois group is Sn. So somehow like formally the Galois group is Sn. And then also, and there's something, this result that sort of you treat the coefficients formally as variables, then the Galois group is Sn. Can be beefed up using something called Hilbert's irreducibility theorem to saying some version of the fact that like now when I actually plug in actual rational numbers for the coefficients, then sort of generically in those rational numbers, I'm going to get the Galois group Sn. That's a little bit far afield from what we're doing here, so I don't want to get into it. But so there, there are various ways this can be made precise, and at least I hope, sort of based on what we've done so far, you can believe this idea that generically the Galois group is Sn. But a priori, the Galois group sort of could be any subgroup of Sn. Like here's one example, the Z mod NZ cross, but it could also be Sn itself, and like there's many sort of subgroups between these two. So let me remark in passing, it's actually an open question, like whether every sort of subgroup of Sn can be realized as a Galois group of a polynomial over the rational numbers. So it's true over, it's always true that over some field you can find it. That's a pretty trivial thing to prove, but if you ask like, is there a polynomial over the rational numbers with Galois group blank? So that's an open question for many groups. That's called the inverse Galois problem, and I don't want to sort of say anything more about that right now. Just to sort of point it out. You want to, so the question I wanted to say is like sort of, the Galois group is sort of something about the roots of the polynomials, whereas, yeah, it's like maybe the question is like how to see this sort of at the level of the roots. and the point actually is exactly sort of this thing I said earlier about sort of roots of unity being special, because sort of they satisfy sort of algebraic relations between each other. So the point is sort of a small Galois group corresponds to sort of lots of algebraic relations between the roots. And really sort of unexpected, because and there are certain relations between the roots that will always be there. I'll make that precise in a second. So the relations are satisfied sort of generically between the roots of any degree n polynomial. But then, so the roots of x to n minus 1 satisfy lots more relations. Because if I fix any one of them, then I can express any other root as sort of a power of that root. So that's some sort of algebraic relation that sort of holds between the roots of these guys. It doesn't hold between the roots of sort of a generic polynomial. And so and you can make this precise. I mean, the Galois group is sort of it is the group of permutations of the roots. Preserving all algebraic relations. Between them. So this is sort of how you can see this connection formally. So I'll make this precise in a moment, but the idea is so the Galois group is sort of the permutation of the root that sort of preserve the algebraic relations. That means if there are more algebraic relations, there are more things to preserve. That means the Galois group is going to get smaller. So, i.e., so say f of x, so now let me work over just an arbitrary field. And let me just take a separable polynomial. It's not so important that this be separable, but let me just take a separable polynomial. Okay. So, and then look at the Galois group of f. So what does that mean? Well, it means take a splitting field. L over K, and then sort of look at hot L over K. Okay, but I mean, what does it mean to have a splitting field? So if I have a splitting field, so if, so I'm looking at the automorphism of K and it's sort of acting on the roots alpha 1 through alpha n. These are the roots of f in L. So when I say the Galois group of f, I mean literally, sort of the automorphisms of the splitting field, sort of as they act by permutations of the roots of f in that splitting field. Well, okay, but so when I have L is equal to K alpha 1 through K alpha n. But really, and so that means that sort of I have an ideal. Right? So that and really what this means, because alpha 1 through alpha n are algebraic, implies that if I take the map from sort of K x1 from xn, if I look at the map from the polynomial ring to L, sending xi to alpha I, then this is surjective. So and of course, if these elements weren't algebraic, then this would not be a surjective map. Like if you had a transcendental element, this wouldn't be surjective. But I think we're doing Galois theory, so everything, these alpha are declared to be roots of a polynomial, so of course they're algebraic. And then this map really is surjective. So that means L is equal to sort of K x1 xn mod I. Okay. So an element of I, like if f is contained in I, that means the f of alpha 1 through alpha n. So if I take this polynomial, which has sort of coefficients in k, and I sort of plug in all of the, sorry, I already have an f. Let me take a different. So in this ideal is something. So f was my irreducible polynomial, my separable polynomial I started with. So let me take g as a polynomial in sort of n variables in I, and then I plug in g of alpha 1 through alpha n, I get 0. So in I is just the kernel of this map, which sends xi to alpha I. So that exactly means sort of if g is an I, then sort of g of alpha 1 through alpha n is equal to 0. But that's saying like g is an algebraic relation between the roots. So then this is really what I mean by an algebraic relation between the roots. I mean some polynomial sort of in n variables such that when I plug in with coefficients in sort of the base field, such that when I plug in these roots, I get 0. Okay. I mean, somehow, like now, what does it mean to give a map? So, like an automorphism of L over K. Well, these are just going to be maps. Like to give an automorphism of K, I have to give a map from sort of L to L. And just any maps, so a map of K algebras. So an L is a field, so it'll be automatically injective, and then it's finite over K, so injective implies surjective. So giving an automorphism over K is just giving a map of K algebras. But that means I'm sort of giving a map from Kx1 from xn mod I to L. And I mean, somehow, I know sort of, so, and let me sort of, so I mentioned there's some trivial relations here. Oh, someone asking a question? I saw a hand raised. Okay, maybe this is accidental. So I know sort of f of x1, f of x2, and so on, f of xn are in here because alpha 1 through alpha n are roots of this. So, I mean, so xi has to go to alpha j, and so xi over here, which I'm really thinking of as being sort of alpha I. So this is just encoding sort of this map that has to sort of permute these roots, but also, but somehow sort of if g is in I, then that implies g of alpha 1 through alpha n is equal to 0. Then sort of I have this map sort of sigma, this automorphism. So to get a map, I need that g of sigma of alpha 1, sigma of alpha n is equal to 0. Okay, so I mean somehow like this, I mean, I don't know, maybe somehow the way I said this is almost like I made something that's tautologically true a bit confusing. But so just the point is sort of if there's some relation, like if there's some polynomial with sort of coefficients in x1 through a polynomial with coefficients in k and variables x1 through xn, such that like alpha 1 through alpha n are a root of it, sort of are a 0 of that multivariable polynomial. Like then just like before, when I apply an automorphism that fixes the coefficients k, then sort of the new thing I get still is a root of that, sort of a 0 of that multivariable polynomial. So that's all I'm saying here. But so, okay, so the point is like, and somehow what you see from this, like in the automorphisms of L over K are just sort of are the permutations of the roots satisfying that sort of if G contained in kx1 through xn is such that G of alpha 1 through alpha n is equal to 0, then after applying this, this permutation, then I still get 0. Like that is the point of this computation. Like somehow, literally, the Galois group is the set of permutations of the roots that preserve algebraic relations between the roots, where those algebraic relations have coefficients in k. But in particular, I mean, in these algebraic relations, so now you can also see sort of the connections between everything, because L is equal to k x1 through xn mod I. This I was the ideal of all algebraic relations. On the other hand, we know the Galois group has size, so the degree of this field extension, and sort of the bigger I is, the smaller this degree. So the more, and somehow literally, the more algebraic relations you satisfy, the more things are in I, the smaller this quotient is going to be, which means sort of this degree is going to be smaller, which means the Galois group is going to be smaller. So somehow you can, if you think about it this way, then you can literally see how algebraic relation, like non-trivial algebraic relations, are forcing your Galois group to be smaller. And so, yeah, and the reason I emphasize this is because I think this is probably closer to the original perspective of how people thought about these things and like what question people were interested in. I mean, somehow, some of the original motivation for Galois theory was like in trying to understand sort of algebraic relations between roots of polynomials. And I think this just gets kind of lost in like this sort of treatment in terms of field extensions and Galois groups. But in really, like this is what Galois theory was originally about. Like Galois theory is about understanding sort of the automorphisms of roots that sort of preserved algebraic relations. And so, and somehow, I like to, and for me, like this is very satisfying to sort of have this perspective on it. And I think it makes it much clearer what's going on. So this is maybe not emphasized in the book or in most sources, but I like to think about it this way. Okay, so I think that's probably a good place to stop for today. I'll stop the video, but I'll stick around if anyone has any questions.